Right now, across this university campus, tens of thousands of devices are broadcasting and receiving data simultaneously. Phones, laptops, servers, and smart projectors transmit. Millions of signals move through the air and fiber optic lines, yet they do not dissolve into chaos. Every single packet of data finds its destination. That precision begins the moment a device wakes up. When a computer science student opens her laptop in a crowded courtyard, the machine immediately begins preparing to join the campus network. Before it even attempts to reach the local Wi-Fi router, the laptop performs an invisible internal check. It pings the address 127.0.0.1. This is the loopback address. The signal never leaves the hardware. It travels through the laptop's own TCP/IP stack to verify that its networking software is awake and functioning correctly. Receiving a response from the loopback address proves the machine is mechanically ready to communicate, but it remains entirely isolated. To connect to other devices, it requires a mathematically structured identity. Network administrators cannot manually type a unique identity into every device that joins a campus network. Instead, the system manages this automatically through the Dynamic Host Configuration Protocol, or DHCP. The laptop secures an identity through a four-step digital negotiation called the DORA process. First, discover. The laptop broadcasts a message asking for an available DHCP server. Next, offer. The campus router replies with a candidate address. Third, request. The laptop broadcasts its formal acceptance of that specific address. Finally, acknowledge. The server verifies the assignment. The negotiation completes in a fraction of a second. The campus server officially grants the laptop a temporary lease, assigning it the address of 192.168.10.47. Through this automated handshake, a silent piece of hardware is recognized and integrated. It is now a functioning node on the campus grid. To understand how network routing works, we have to look past the decimal numbers. An IP address is a structure of exactly 32 binary bits broken into 4 octets. Network engineers use CIDR notation, classless interdomain routing, to divide these 32 bits into 2 distinct groups. For this subnet, the notation is /24. This means the first 24 bits, marked here in cool blue, form the network prefix. The final 8 bits, in warm amber, act as the host identifier. This functions like the postal system. Routers read the blue network portion like a zip code to deliver data to the correct general neighborhood on campus. Once the data arrives, the local switch reads the amber host portion like a specific house number to find the exact machine. CIDR notation allows network engineers to slide the boundary between the network prefix and the host identifier. They can size a network to fit their exact needs, preventing the waste of thousands of unused addresses. On a macro scale, the computer science department operates inside the 192.168.10.0/24 subnet. This configuration provides 254 usable addresses, enough room for a large lecture hall. An administrative office across the hall only has 20 devices. Giving them a /24 block would leave hundreds of addresses empty. Using variable length subnet masking, engineers assign that office a much smaller /27 subnet. They carve out a block of 32 addresses, reserving the remaining space for other departments. Keeping these departments on separate subnets isolates their traffic. If a massive data transfer overloads the computer science lab, the congestion stays contained within its designated boundary, protecting the administrative network from slowdowns. When multiple users need the same data simultaneously, the network relies on the 239 administratively scoped address block. This is multicast. Instead of a server sending 50 separate copies of a video lecture, a single stream splits at the routers, delivering the feed only to the specific nodes that requested it. Subnetting and multicast form the architectural walls and express lanes of the campus infrastructure. They allocate space efficiently and route data cleanly, keeping a high-traffic network running smoothly. Eventually, the student's laptop needs to access an external website. It sends a request out to the internet. But there is a technical hurdle. Its address, 192.168.10.47, is defined as a private IP. Internet routers are programmed to drop traffic originating from this range. These private address blocks exist because the original IPv4 protocol maxed out at roughly 4.3 billion public addresses. When the global supply was exhausted, private ranges allowed institutions, homes, and businesses to reuse the same numbers internally. Here, the private network meets the public web. The router uses network address translation to replace the private address with a public IP. In the NAT table, it attaches unique port numbers, like 32,628, matching external responses to the correct device. This translation process extended the life of the IPv4 protocol for decades, allowing the Internet to continue adding billions of devices, even after the public address pool was exhausted. The long-term solution to address exhaustion is a newer standard. IPv6 uses a 128-bit hexadecimal format. Instead of 4 billion total addresses, it provides 340 undecillion, enough unique identifiers to assign a public IP to every device we could realistically build. Because IPv4 and IPv6 devices cannot naturally understand each other, modern routers utilize translation mechanisms like NAT64 and DNS64 to bridge the gap. They convert requests on the fly so legacy servers can communicate with the new standard. From the first internal loopback check to the scale of global translation, these addressing schemes provide the logic required to identify, isolate, and connect every device on a network. It is the structural framework that ensures every packet of data arrives exactly where it belongs.